So take it away, Alex.
All right. Yeah, thanks for that introduction. Yeah, so high-level modeling and solving for online and real-time combinatorial optimization. Let's dive in. Right, so I should first mention that what I'm talking about here is based on 2 published papers that are published together with my supervisors during my PhD candidature. So if you want more information, you can have a look at those. And if you're wondering, right now I'm writing up my thesis. All right. Yeah, so we are from different backgrounds and things like that. So I think a good idea is to start with some terminology here, so we're all on the same page. When I say combinatorial optimization, I mean finding an optimal combination of decisions. Examples of this are vehicle routing and scheduling. Usually we're talking about discrete objects from finite sets, and brute force search is completely infeasible, so we need to be smarter than that. When I say modeling, what's a model? Well, that means specifying the problem without specifying how to solve it. We should do this with parameters and variables, that the variables are our decisions. We have constraints in those variables, and we have an objective, some goal. Ideally, this is in high-level language, such as Minizinc, and also a solver-independent language, where we can write the model in some mathematical way, and then we can say, oh, I want to use a mixed integer programming solver, or I want to use a local search solver, or a constraint programming solver. Right? This allows rapid prototyping, and because of Minizinc does a lot of smart things, this is also efficient, and this is all very accessible because of this. When I say solving, I mean finding an optimal solution given a model and their parameters, right? So we need to provide the parameters. And we assign the variables, we satisfy the constraints, we find an optimal objective. We usually do this via search, inference, and heuristics, things like that. All right, let's look at an example, job shop scheduling. And we'll come back to this example throughout this presentation. So suppose we have 2 machines, right, that we want to schedule tasks on, and we have some kind of dimension of time, of course. We have some tasks here. We have the orange job and the purple job. So the orange job, 1A here, means that's the first job needs to go on A, and it's that size, and the second job, 2B, needs to go on machine B, and it's that size, right? So we can schedule them down there like that, right? So none of them overlap in one machine, and we need to complete the first job before we do the second job, right? And then we want to complete this as early as possible to minimize the make span. Now let's quickly look over how we model this in Minizinc so we can understand the high level and the accessibility of this, right? So first we want to define our objects, or the objects that we're talking about, right? So first we have a set of machines, we have a set of jobs, we have a set of tasks, and here I just wrote that the tasks, we coerce the task from the machine because we have 1 task per machine, so we can write it like that. We have some parameters here, right? So what's given the job and the task of that job. What's the task duration? What is the machine requirement, right? What machine does this task need to run on? And here we have our decision variable. What's the start time of this task, of all of the tasks? And then we have some constraints. So I won't bore you with all the details here, but basically the first constraint says the precedence needs to be enforced. The second one says that there's no overlap. And the third one says just minimize the make span. All right, so to reiterate, that was quite high level. And of course, that's a mathematical language in some sort. So we can use this with either a mixed integer programming solver or a CP solver, etc. Rapid prototyping, efficient and accessible, as I said. Now let's throw in something into the mix that can complicate things. Uncertainty and dynamism, right? So usually there's 2 assumptions in conventional optimization, especially combinatorial optimization. The first one is that the definition of the whole problem is complete. There's no uncertainty, there's no kind of question marks. There's just, oh, here's everything. The second one is that details do not change over time, right? So everything is known beforehand. And as a consequence, we can solve this in one go. I mean, if time permits, of course. We call this offline optimization because we just look at the whole thing, look at the whole problem, all the information, and we try to come up with a solution. But this does not often hold in practice, these two assumptions. Think of scheduling, right? In the real world, often more jobs arrive over time, but we need to schedule the tasks that we know about now, right? We don't want to sit and wait around until we know all of it, because then we're going to be way in the future, right? So we want to schedule things now, but maybe something will show up while we're scheduling and running these jobs. There could also be uncertainty in running time. And maybe a job runs longer than we expected to, and now the schedule is disrupted. Vehicle routing. Think about rideshare and pickup and delivery. Right? I like the rideshare example because if you remember before the pandemic, we had Uber and things like that, where you could actually do the rideshare and where you could jump in the middle of someone else being transferred from one position to another. You can jump into the car in the middle of that and then be dropped off on the way when the other person is getting dropped off, right? So this can complicate things a lot. And of course, where's the dynamism and uncertainty? Drivers can join and leave the fleet at any time. Customers can pop up at any place, and maybe we wanna have an optimal route in some fashion here. So there's a lot of disruptions that can happen. Energy systems, right? Supply and demand, wind and sunlight, things like that. I mean, we can of course predict these things, but no prediction is 100%, right? So there's still some wiggle room that we need to maybe react to, or we need to handle in some way. Robotics, another example, constantly changing environment goals when we're walking around. So how do we address uncertainty and dynamism? I like to divide it up into two camps. We have the predictive camp and we have the reactive camp. And of course, I'm dividing it here, but of course, we can combine them if we want to get really advanced. But let's look at them by themselves. The predictive one, we want to predict all the possible things that can happen. Right, so here we have stochastic optimization or robust optimization. Right, so we're creating a policy tree of solution, right? So if this, then do that, and if that happens, then do that thing, right? We optimize for the expected case in stochastic, and we want to make sure that it's likely to work regardless of what happens in the robust case, right? But this requires us to really understand the possible events, the probabilities, the distributions, requires expert analysis. Maybe you can use AI here in some machine learning thing, I don't know. And also, if you have too many events and things, I mean, there could be a combinatorial explosion here just talking about the prediction, right? Because there's so many things that could happen. There's so many different responses you could do. So this can be hard and tough and can be very time consuming in a lot of cases. On the other hand, we have the reactive approach, online optimization. This is an iterative and reactive approach. Data arrives over time, maybe even during solving if you're in a real-time situation. And as I mentioned before with the scheduling, we take some irreversible decisions now before all data has arrived, right? Because we're kind of solving on the go, right? This requires very little analysis on the other hand. We just set up the rules and click run, right? So I like to call this the rock and roll mode, right? You just rock and roll. Right, and we want that because that can be very powerful in a lot of situations. Now, let's look over the objectives and motivations of the research that I'm about to dive into. So the observation online optimization is often needed in practice, but the main problem is that there is no problem-independent modeling and solving framework for online optimization. What do I mean by that? Well, of course, online optimization has been around for a long time. There are specialized algorithms and frameworks for particular problems, but what if, as we often like to do in combinatorial optimization, what if we want to throw in arbitrary constraints here because we think that's better and we want to model the real world in a different way that maybe better reflects it, or we have another situation? yeah, then these specialized algorithms maybe don't even work at all, or are really slow, or whatever, right? What about using minisync? Minisync is high level, minisync is general, right? Well, we can use minisync, and that's actually what we're doing. We're extending minisync in my research here. But just using minisync from the start requires a lot of ad hoc scripting and or obfuscating model reformulation, and it becomes really messy really quickly to make sure that this thing run, right? And I don't call that high level. And high level is what we want, right? We want high level. We want solver and problem independent. We want to allow rapid prototyping. We want it to make it efficient. We want to make it accessible. And we can also use this approach to decompose large-scale static problems with kind of rolling horizon decomposition. So we want to extend minisync to allow this. Now let's look at the key problems. What are the key problems? Well, the first problem is, how do we combine new data with the incumbent solution and the current data? Right, new data regarding new decisions constantly get added. Disruptions affecting the current decisions can happen at any time. So that's one key problem we need to address. The second one, how do we keep track of what can and cannot be changed? And how things can be changed if they can change, right? Maybe there's some restriction. Well, you can change this a little bit. But what does that mean? We cannot reschedule the departure time of a train that is already departed, for example. We cannot change the departure time to yesterday, right? So there are restrictions here. And how do we formalize that? And also, here's the big one. How do we perform automatic garbage collection and aggregation to increase performance? Right, the size of the instance grows with time as new data arrives. Garbage and irrelevant data can pile up. This, of course, slows down compilation and solving. Some variables and data are realized. This means that they will not or cannot change again in the future. And an important thing to note that this is not the same as garbage collection in programming languages, right? That's just a different thing, but it's kind of in the same vein. So I'm using the same language there. And of course, the final question is, how do we transform all of that above into some kind of mid-level, right, pure minisync, so we can just run with all the solvers we love and use on a daily basis? Right, so let's look at today's outline. First, I'm going to look at some examples and key concepts. Then I'm going to look at adding objects and decisions ongoingly to our instance. Then I'm going to look at restrictions on what can be changed and how, plus disruptions, how that affects things. And we're going to look at rolling horizon decompositions. And then we're going to go into the garbage collection territory. So we have realizations, identifying what can't and won't change anymore. Aggregation, reformulating constraints to allow more garbage collection. And garbage collection itself, removing the unused data. And then we're going to look at results. All right, so before I dive into all the details, if anyone has any questions now or any question marks or is confused about anything, feel free to speak up at this point. So any questions?
Yeah, maybe I have one, Alexander. Can you just, because I think you're going to talk about it a lot, can you just say a little bit more about garbage collection, the concept of it? Give us an example of what kind of irrelevant data, how does data become irrelevant in this online thing? Yeah,
so let's say we have a scheduling problem, right? And we always get new jobs constantly get added to the system. But it's not right, but I mean, you and I, we clearly know that, oh yeah, this job is done, it's finished, we can throw it away, right? But that's not as clear when you're working with a generic framework. You need to have some kind of analysis, when are things done and not done? And can we just remove it? What about if we have some global constraints that kind of breaks down if we just remove things? We need to make sure that all the constraints still mean what they're supposed to mean. And only things that can be removed actually are removed.
So you're really talking about, like, there's a moving window and how you keep that window.
Yeah. Kind of like, how do we throw away things at the end of the window?
Okay, great, thank you.
Yeah.
So Alexander, I have one question. So in the dynamic setting, So suppose, let us take an example of this Uber kind of setting. So I have taken maybe one passenger and I have given him or her some estimates on when he will arrive there. Maybe if I have a couple of passengers, I have computed some kind of optimum, right? Now one more passenger is added. Now that is going to change the say arrival time when you will take them to their destinations, right? So when you are talking about optimization, what is your objective functions here? Because this will continue to change, right? Your optimum, and so which optimum you wants to compete against?
Yeah, so I mean the objective could be anything, right? So I'm not locking us into any specific objective. I want to make this a general framework where you can use all the objectives that you want. But one example of an objective would be to have kind of minimize wait time for the customers, for example, right? And then if we can pick someone up on the way, then their wait time will be very little because we just pick them up directly. And maybe we also want to minimize at the same time. There's a kind of a multi-objective thing going on. We want to minimize the driver driving unnecessary routes, things like that.
No, but so you have computed initially one route, right? And then if suppose new person, he wants to go there, and that route maybe has to be deviated a lot, right? So so how will you like initially whatever your estimates were, that will change a lot, right? So how do you kind of have this kind of optimum?
Yeah, so I mean, because this is online, like the actual problem itself is online, it will change. There is kind of a theoretical oracle optimum, but that can be hard to calculate, right? If we know everything that would happen in advance, then we could plan much smarter, right? But that's not, we can't use that in the reality. So I'm not trying to compete with any specific algorithms for that problem. I'm just
so in the online algorithm setting, there is a very well-known notion of called competitive ratio, right? So where you are competing with the offline optimum, right? So there is a opt, which is like if you see all the inputs, there is optimum there. So are you also trying similar things, or you have a different notion of competitive ratio?
Yeah, so I'm not working anything with the competitive ratio here, because of course it depends on the problem, right? Because this is a general framework, it all depends on the problem of what kind of competitive ratio you can reach. It depends on what kind of constraints you have, on what kind of time windows you have, right? So there's a lot of parameters that you can play around with within this framework that I'm presenting here. So I can't really, I mean, I probably could derive a super complicated mathematical formula, but no, I haven't done that.
I think what you're looking for is, he's doing optimum with respect to an objective given in the model with respect to the knowledge we have now, right?
Yeah.
And then when new knowledge comes in, we recompute the optimum.
Yeah. So I mean, we have an objective value. So you can, of course, well, if that's what you mean, how do we like put in kind of slack in the objective value to make sure that we don't myopically over optimize? That's of course one thing we can do. I'm not doing any of that. My framework currently is purely reactive. It just the information we know, we're trying to optimize that as well as possible. And then as soon as change happen, we react to that.
Okay, thanks.
Can I just ask for a clarification? Peter was saying that there's a known objective. Does that mean the new information is only affecting the constraints, only affecting the feasible set? You don't have any new objective terms?
No, I mean, we know what the objective function is. It doesn't change.
Yeah, so, so the objective function could depend on objects that get added over time, right?
Ah, okay, yeah, that makes sense.
Yeah, but kind of like the general structure of the objective. I mean, you can probably use a huge if then else thing to make some weird stuff, but generally what we've been talking about in this research is we have one objective value and that stays constant throughout.
Yeah, thank you.
All right, hopefully that cleared up some of the questions you have, and let's now dive into some examples and key concepts. So let's go back to this job shop scheduling problem, but now instead we're looking at it from the online optimization lens. So we have some problems arrive and we have kind of a session start time. When I say session, I mean solving session, right? because we need to divide this up into iterations, right? As I said, we have an iterative and reactive approach. We have first iteration, the orange jobs get added to the queue, and we need to do something with them. In the next iteration, the purple jobs get added, and we need to schedule them somehow, and then third, fourth, etc., iteration. And this can go on forever, right? So how does this look like? Well, assuming that we're in a real-time situation, this session length is very important, right? Because the more time we spend solving, that time also ticks in kind of real life or in the simulation or whatever the thing is we're connecting it to. We're trying, right? So, but if we're not in a real-time situation, then the session length is basically 0, right? Time stands still while we're solving. But let's assume we're in a real-time situation. This is then the forbid zone. Right? We're not allowed to put anything here because before the session ends, right, we're allocating this much time, and maybe it is faster, but we still have allocated this time. And then if we take longer, we're not allowed to, right? We're not allowed to take longer. So we have a timeout before this session end. Right? So we know we're boxed in. We know that, okay, this is the framework we're working with, the viewpoint. So we forbid everything before the session ends, because when we come back and say, hey, these are the decisions that I recommend you should do, you should have done this an hour ago, right? That doesn't really work. We want to know what to do now and in the future. So that's why we need to forbid that and put the scheduled things here. Next iteration, right? The session ends and the start time, etc., moves forward. We have the purple jobs come in. Now we can reschedule one of the orange jobs, but the other orange job is in what we call the commit zone. It has already started, right? We can't, right? And here we're assuming that the jobs cannot be canceled in the middle, right? Assuming that the job needs to be run to its full completion, we can't change this here, right? We can't just come and say, oh, don't do that you did an hour ago, right? The commit zone. But that job here, we can change. So we put those jobs in there, those tasks in there, and then we move on, right? So there's what can we change, what is not changeable, right? So we can see kind of how that picture comes together. Now, how do we model this in our framework? So remember this is the job shop mini-sync model that I showed you. I've grayed out a few things here that we actually don't need to touch in our framework. There are some things that are highlighted here in red. That's the new things that we need to add in, right? So this is the idea of high-level modeling. On the jobs enum, we add an online annotation. This basically means new jobs can get added at any time. On the start time decision, we add a time variable, or not a variable, sorry. We add a time annotation to signal to our online optimization system to say that this is a decision that regards time, right? This is a time variable in some sense, right? And how does that work in practice? So this, what you're looking at now, this is the standard mini-sync kind of data flow.
So Alexander, sorry, I have a question on that session slide. Can you please go there?
This one?
No, the earlier one, the picture. Yeah, so I really did not understand the motivation and the rationale behind this. I mean, so first of all, how are you determining the length of these sessions? And also, why cannot we schedule any of the jobs in those, like, why have you blocked them? I didn't really get that.
The session length is the time we've set aside for solving the optimization problem. So the solver's running from the start to the end, and all new decisions have to be after the end.
Okay.
Yep.
Right. So if we're looking here, what decides the session length? Well, that's up to the modeler or whoever, right? this is kind of an analysis thing. What's the appropriate session length to get good performance, to get a good solution in the end? So that's not kind of inherent to the problem. That's more of the solving. Why?
So as Peter said, this is the time taken by the solver to solve this problem, right? The session length.
Yeah, and
okay.
and then because we're real time, the time ticks in the kind of machine scheduling world and the optimization solver world. They are synchronized. They tick at the same time, right? So we're planning as the clock ticks in some sense. So that's why we need to have these restrictions. Is that clear?
Yeah, now it's clear.
Right, so, okay. The Minisync data flow, right? So we have a model, we instantiate it, we then get an instance, we solve it, we get a solution, right? But in our online framework, it's a bit different. The solution feeds back, and then we solve again with new data, and then it feeds back and we solve again with new data, right? So we have an ongoing iterative process here. But hang on, what about this model thing here? Surely we can, it's not just about adding a few annotations, then it works. And no, you're right. We need some model transformations, and these are things we have developed. So the only thing you as a modeler need to do is to put these annotations here. Then we are doing the work for you, adding these transformations in the background before all the solving starts. So this online annotation basically means that, okay, we have some old jobs and we have some new jobs. So we need to create those enums. And then the set of jobs is just the set of old jobs and new jobs, right? Here are our parameters. Because the jobs enum was annotated, we can automatically see here that the arrays that are indexed by jobs also needs some kind of transformation. So here, for example, we have the machine requirements. We have the machine requirements for the old jobs. We have the machine requirements for the new jobs. And then we need to add them together to make the requirement, right? And I'm cheating a little bit here. It's not as simple as just doing requirement old plus requirement new. There is a lot of mapping and coercion thing going on here to make sure that the right object refers to the right thing, right? But that wouldn't really fit in the slide. So just remember that there are some extra mapping and coercion going on there. And this is analogous for the duration array. Now, what about our decision variable, start? We added the time annotation. And then in the background, a constraint gets added to our model before it gets sent to the solver, right? So this constraint basically makes sure that our forbidden commit things are upheld. So what this constraint basically says is, for all jobs and for all tasks, if it's already been scheduled, if the task is in the past, then we commit it. Commit meaning it needs to be this forever in the future. Else forbid the past. This means that when if we put it somewhere, it needs to be now or in the future. We can't put it in the past, right? You might notice that we're using some cool things here. So sol of x, that means the value of x before solving started is available. Has sol, that means whether sol of x is available. So we can use that as a kind of guard. And then we have kind of the functions s beginning, s length, s end to obtain the session beginning, length, and end, right? So we can imagine how all these things work together. Now, the constraints can be left as is, right? There's no rotation needed there, and there's no transformation needed there, right? In most cases, they can be just left as is. Now, we've kind of expanded this question mark a little bit, so it actually looks a bit more like this. So we have our offline model, we have our annotations, transform that. It becomes kind of an online model that is hard to read, hard to understand, because there's a lot of weird things going on. But it's written so that it works and does exactly what we want it to do when we solve it in a loop like this. So this is how we can get the high level thing transformed into kind of mid-level thing and then solve it. All right. Here is another example. Let's say in our job shop scheduling problem, we have an extra decision. Suppose we also need to assign a supervisor to each job before it starts. So here we have an enum of persons, and let's say the persons are, we always have the same persons, so this is not online. We have an array, given a job, what's the person that is the supervisor here? Right, so here we need to add another annotation. So this means that we need to commit this variable at a specific time, right? We are free to change the supervisor of a job that has not started, but if it has started, then it's committed, right? And this is exactly what this annotation says. So we're mapping, we have the array in the commit var at, and we have the array here. So we're kind of mapping index to index that the start time for J and min tasks means the first job, right? So the first job, sorry, the first task of that job is the time when that starts. That's the time when we can also commit what supervisor this job had. How does this look like in actual constraint form? Basically, if already assigned, and if already scheduled, and if in the past, then commit, right? And notice that we don't have any forbid statement here, because it's basically it's just not needed here, because we're always free to use all the persons, and we're always, and the job cannot change weirdly, right? So it follows the rules quite nicely here. But there's more, of course, than just these examples. We can have multiple online annotations, and then things can get crazy, but it works. We can have variables regarding time and affected by time, as I showed you. We can have commit and forbid separately or in combination. We can have, we can do commit and forbid on variables, array indices, domain values of a set / array of variables, right? We can do offsets as well. So if we have a specific commit or forbid horizon, maybe we want to assign that supervisor 10 minutes in advance, and then it should not change. We can have that commit horizon. And of course, we can define our own commit and forbid-esque constraints using the constructs that I've shown you. But what about disruptions, right? It seems that it seems like that's a missing puzzle piece, right? So this is how our current framework looks like. Where are the disruptions? They're not here. Well, there, I added them, right? So it's this simple, actually, right? So instead of just feeding the solution back, in most cases, we have some simulation, or we have the real world or something where there's uncertainty in execution. The solver is not it doesn't say this is what's happening. The solver is more of a recommendation system. This is what you should do. And then we go to the simulation or to the real world and try to do it as best as possible. And there's some things that didn't line up properly. Maybe there's some delays. Maybe there's a machine that broke down and whatnot, right? So the current environment comes from that, right? So instead of just the solution, we go through the actual thing, we get the current environment back, but the rest of the system works the same, right? So the system doesn't really know if this is just the solution that they got back, or if it's an updated view of the current environment. It will react properly either way, because all the parameters will have changed. Things that have started, they were in the past. Things that were planned to be started but isn't, well, they will of course not have started in the past, right? Because it needs to reflect the current environment. Right, and then also let's quickly look at rolling horizon decomposition. So let's look at our job shop example again, but instead of making this kind of an online, dynamic, whatnot problem, let's just say we have a huge job shop scheduling problem, and we want to use rolling horizon as kind of a meta heuristic, or whatever the word is for it. Then we can, the idea is that we should be able to annotate the solve keyword there. We want to decompose it by index, right? What do we want to decompose? We want to decompose the enum jobs. For example, what's the size? It could be 10, right? So we are always looking at a window of 10. Well, how much is the step size? Well, at each iteration, we look at 4 new and forget 4 old. Commit the 4 old, add 4 new, right? And the selection process, we could have different selection processes here as well. So in this example here, it's random. And it's interesting because it overlaps, but also the rolling horizon case is different because here the modeler can choose how things changes. In the dynamic and uncertain case, we need to react to the changes. We need to follow by the changes rules. Here, we rule the changes. So there's some interesting things here. We can also decompose by time if we want to. All right, so now we've ticked off the first 4 things. And now it's just the garbage collection stuff left. But before, again, I dive into the garbage collection, it's important that we fully understand what we've just covered. So are there any questions? There's some time for questions. Are there any confusion? Do you want any clarification before we dive in?
Go ahead, Alex.
Yeah. So it looks like there's nothing in the chat and no one has any questions. Perfect. Let's then dive into garbage collection. All right. The first question you might ask is, why do we need garbage collection, right? Improve performance, sure, but is it really that important? Well, this graph may prove a point. So we tried running without garbage collection and with garbage collection. And this is and the orange one is instantiation time per iteration. And the purple one at the bottom is with garbage collection, right? And this is right. This is per iteration. This is not kind of accumulated sum of how much time we spend. This is per iteration, right? So you can see that it quickly explodes if we don't remove the old and irrelevant data. The size of the instance grows, slows down processing, but as I mentioned before, some data and some variables are realized. They will never change or they will never be used. So can we remove them? Removing them automatically in a problem-independent way is not straightforward, but let's try and dive in anyway, right? We want to solve this problem anyway, even if it's not straightforward. Or rather, that's why we want to solve it. If it were straightforward, it wouldn't be a research paper. Okay. We need an incremental and cumulative process, right? First, we want to identify the realized data and variables. Here the model help is a little bit required. Then we want to do some aggregation. We want to summarize the effect of the realized data and variables. And how do we do this? Well, first we need to find what can be aggregated. Then we need to redefine the constraint itself to allow aggregation, but still maintaining so that it means logically the same thing. And then we define an aggregated value that can be passed over to the next iteration and the next iteration and the next. And then, of course, the actual garbage collection, which means filtering of all data. And the aggregation approach here will make sure that there's some, after the aggregation, there will be some unused data lying around. Then we can collect them with garbage collection. Okay, let's first look at realizations. This is an important concept, right? So let's first look at variables and data. So either it has happened, right? If it has happened, then it's realized. So this means that, let's say the arrival time, let's say we're driving cars here, we're driving a truck. When we arrive at node N, that decision is realized when the arrival time is, it should be less than the end, right? So that means that when it is in the past. Or it will never happen again. Travel time between two nodes that are guaranteed to be never used. Right? This information needs to be given by the modeler because it's problem specific. It's really difficult for Minizinc or some kind of automatic system to infer what the model auto represent in the real world or something like that, and from that draw conclusions of how realizations work. So we need to provide this. Essentially, this is the only problem-specific part of our garbage collection method. Now, what about objects? Well, so I talked about enums, and enums and objects, you mean the same thing, right? We have name on the objects, and the objects are what we index into arrays, what we do for loops over, things like that. So each variable in data is then, if it's part of an array that grows or shrinks with time, each variable in data point is then associated with a specific index, and that index is a particular object. So it makes a lot of sense then to talk about, is this object realized or not, right? So the object n is realized if all variables and data indexed with n is realized. This also includes indirect usage via structured object sets or weird coercions and things like that. So we kind of just trickle that information down or trickle it up, whatever the direction should be. And how would this look in Minisync? Well, we could have an annotation that says realize at. So we would just provide then a Boolean, an array of Booleans. Is this realized or not? And then we can apply multiple of them. If one of them is true, then it's realized, right? So we could have one for has happened and one for will never happen. All right, let's look at aggregation. So as I said, we want to summarize the effect that realized data and variables has on the future. Find what can be aggregated, redefine the constraint, introduce the aggregated value, right? And we want to reformulate the model to automatically calculate this during compilation, right? If you remember the data flow picture, in the instantiation phase, that's where the garbage collection takes place, right? So it's part of Minisync compiling things down to something that the solver can understand. And that's where we remove things. And then when the old data gets passed back, it's garbage collected. All right, let's look at an example here. Let's say we have a constraint that looks like this. So it's a sum. 0 is equal to the sum. Ci is a constant indexed by I. So let's assume that that's, or I mean, it could be updated because of disruptions. So we cannot always assume that that's realized. We have xi, that's a variable. So we can also not assume that that's realized at all times. But we can do some quick analysis. And let's say we did the realization analysis that I talked about earlier. We can divide this index set I up into realized and non-realized. But the orange one here is the realized one. Because it's realized, it will never change. That sum will for all, always, for all time in the future, be the same thing. So we can replace that by just a simple integer, right, in this case. Let's say ag for aggregated value. We go on to the next iteration. Our constraint looks like this. Now things may have changed. So there may be new realized things, right? Maybe added new things. Things that were already there may now be realized. So we need to do the same analysis again. We do the realization analysis, as I showed you, and we can split this up into two sums, the realized part and the non-realized part. Again, we replace this by the aggregate value, and now you may see the general pattern, right? In general, a sum constraint would look like this, right? 0 is equal to the aggregated value plus the sum of non-realized things. And then we add on this aggregated value and define it as the sum of the realized thing in this, right? So this is the in any particular given session plus the aggregated value from the previous session, right? So this makes sure that the aggregated value cumulatively adds up, and the constraint itself always means the original thing if we would have kept all that data lying around. All right. We can look at a more complicated example. Let's look at circuit. Right? So if you're not familiar with the circuit constraint, it means that you enforce a full circuit of nodes, I, and I here is indexing X, where Xi is the successor node of I. Right? So basically, okay, here's a node. What's the next node? what's the next node, what's the next node, what's the next node, and then in the end you should end up at the same place you started, and you should have reached all the nodes, right? That's what circuit means. So we want to enforce this in our model, but how do we garbage collect it? Well, we need to use short circuiting in this case, right? Because global constraints themselves are much harder, and we need to do some more analysis. We need to do some more tricky understanding here of the actual global constraints. Luckily, if we solve the aggregation for one global constraint, we can use that all the time in all our future models where that global constraints appear again. So let's look at circuit. It's done via the short circuiting method. So you can see here on this on the one side we have the A graph, and on the other side we have the B graph. Now, let's suppose that C, D, and E, with the double rings around them, that they are realized. We can remove D and E, right? Because they are in the middle of this realized thing, and we can remove them, assuming that all the other constraints and aggregation rules are fine with it, but let's assume that. But we cannot remove C, even though it's realized, because some A must point to C. And you can see here in this example, A pointed to B, now it points to C. So these kind of dotted arrows means that it's not realized, it could change, whatever, it's not committed. But the C is. So we do an aggregation and say C, because C can't change what it points to, it always needs to point to D. Having D lying around is unnecessary. We can just point it directly to F. And of course, all the other aggregation rules of, I don't know, of a travel distance or whatever, will have a similar logic to make sure that the travel distance also is maintained, right? So we can here remove the two nodes in the middle of this thing, or I mean, it's always in the middle in a circuit, right? There's no, a start and a finish in a circuit is kind of arbitrary, right? And of course, this can get very complicated depending on the constraint. Well, what kind of constraints do we have? We have some, we have for all, exists, all different, cumulative circuit, etc., etc. These kind of constraints can all be aggregated. There are some constraints that cannot be aggregated by themselves. So if you have sort or if you have element, when you add a new object, anything in sort can change, right? So we need to apply some extra rules. Often these constraints are either used as part of a bigger constraint, right? So if you kind of decompose circuit into some sort of smaller constraints, you would see an element constraint in there. So that's why it's important to have that high level view where we know it's a circuit. So we can do that aggregation I just showed you. The other reason why maybe sort or something like that is used is to enhance performance. There could be some symmetry breaking and things like that. And this is not critical for correctness, right? So we do not aggregate these and we only impose them per session, not across session. And then the garbage collection will still work and the aggregation will work, right? Now, let's look at some results. So, real-time job shop scheduling. What if we just add jobs continuously up until we have 1,000 or more jobs? This is one of the, this is kind of a modified version of one of the Minisync benchmarks, where there's some job shop problems, and I just kept adding. So in the table below, we see an interesting trade-off that I like to call the meticulousness quickness trade-off. Right, spending too little time in online real-time optimization. And important, this is real-time optimization, right? We don't really have this trade-off if it's not real-time. But in real-time, spending too much time will lead to no or a bad solution. As you can see here, when we have 8 jobs in that column, if we only have solving duration, that means how long is the session. So if we only have a quarter of a second or half a second, we basically get no solution. The jobs piles up too quickly and we can't handle it. It breaks down. The solver can't handle it. So there's no solution at all there. We also see that for 1 second, I mean, it works, but if we go to a higher number, it looks better. Why is that? Well, because spending just the right amount of time, we get a good solution. but we can't just increase the time we spend more and more, right? Because if we spend too much time, things will be executed too late. We're not quick enough. We're sitting there thinking, what's the best way to schedule this? And then 1 hour later, this is the best way to do it. But we could have just said, we couldn't just sit there for 5 minutes and get an equally roughly good solution, but it would be executed almost an hour earlier, right? So this is the trade-off. You can see here that for the 4 jobs per second, that's usually kind of simple. So we don't need that much time. That's why the half a second is probably the best. 8 jobs, a little bit more complicated. So it seems like the 4-second one is the best, right? And this is, of course, a parameter that the modeler need to play around with to understand what's the best one to use for their particular application. We've seen this, but now I'm also showing solving time per iteration, where we have garbage collection with and without garbage collection. So we can see that we saw that the instantiation time just shoots away without garbage collection. And we also see that the solving time slightly rises without garbage collection. Important thing to note with garbage collection, right? If more things are added quicker than we can garbage collect, then we will get this kind of behavior sooner or later, right? But if we can garbage collect roughly the same speed as new things are added, then we will get kind of the flat behavior, more or less. Right, so that's an important thing to keep in mind. If the problem by its nature just grows and grows and grows, it doesn't matter how much garbage collection we do, probably maybe something worth looking into if we can do a lot of radical simplification in such situations, but nothing that I'm aware of. So these are the garbage collection results here. We also have the some other garbage collection results here. So let me explain what's happening here. Let's say we're doing job shop again, but we have one very, very, very extremely long task. If we have no garbage collection, as we saw before, it will clog up the system. We just have too many jobs floating around. It will take too long to compile and everything, so it will time out. Let's assume we have kind of a simple garbage collection, and this is something that we developed earlier. In job shop, we can do some kind of reasoning that, yeah, if here we have the list of jobs. If the first one, index number 1, if that job is done, right, then we can just remove it, right? Because sure, the make span will be wrong, but we can still, it will still optimize the correct thing, right? So we can do kind of a simple garbage collection, but because of this very long job, we will look at some point, we'll look at index 1 at this humongous job, and we will not be able to do anything. So we need our garbage collection here. We can kind of look at it kind of like, okay, bounds consistent versus domain consistent garbage collection if we want to use CP terminology here, but I'm not sure how you would apply that. But you see the difference here. In our garbage collection, we can remove arbitrary objects anywhere in the list of objects. So, and you can see here, we can just keep running and it still maintains rather small compilation time and runtime. All right, to conclude this talk, what I presented here is the first problem-independent framework for modeling and solving online and real-time combinatorial optimization. This is declarative modeling, right? So we call this online minisync. We've extended minisync, which already is declarative modeling. So this is all declarative modeling. We can use off-the-shelf solvers, all that are supported by minisync. This is an important step forward in modeling online problems. We systematically infer realized data, variables, and objects. Modeler must provide some basic information, but we handle the rest. We do automatic transformation to a language that can be compiled with regular minisync compiler. And we also look at how to aggregate and garbage collect from constraints. Right, the future work here is kind of creating an aggregation library that can automatically look at your model and see, okay, you use that constraint, that constraint, that constraint. That means that it should be rewritten like this, bam, right? So kind of a library of all the different constraints you can imagine and how to aggregate them. And one more time, this then allows for rapid prototyping, and this is efficient and high level, and it's accessible, right? So hopefully that was interesting. Are there any questions?